Good morning, everybody, and welcome to this seminar on from the Open University as part of Maths Week Scotland. My name's Andrew, and I'm a member of staff at the School of Maths and Statistics at the Open University. So today we're going to have a talk from Ivan Sudakov, who also works at the School of Maths and Stats at the Open University, and he is going to talk to us about using maths to understand the role that melting of the sea ice is playing within climate change. So I'm going to hand you over to Ivan, who's going to talk to us about this fascinating topic. Ivan.
Yeah, thank you, Andy. So this is very nice morning, and let me share my screen, and when we are going to begin. So the goal of this presentation, I want to show you a single equation that can help to describe a beautiful sea ice structure. So just pay attention. I'm offering actually free equation during this presentation, but pay attention to the main one. Okay. So also I want to say thank you to the United States National Science Foundation for support of this work. All right. Actually, you know, and everybody knows that climate is changing and rapidly warming, and it's a big problem, especially in the Arctic region. And main people who study climate scientists, geoscientists, were really aware what's going on. But there is a broad community of scientists, especially, for example, in physics and mathematics, who can contribute to this research. We can contribute at some kind of fundamental level, because we still don't understand many processes in the climate system and why climate change is happening so rapidly. And this is the idea. If you want to choose in the future your what to do, and if you like physics and mathematics, you can be you can have a look at climate change problem too, because to solve these problems we need really strong, rigorous math and good understanding of fundamental physics. And in my presentation I will show you how to use both physics and mathematics to study sea ice particularly. And let's just recall what is sea ice and what is Arctic sea ice. So this is the northern hemisphere, and definitely it's frozen because this is so-called the North Pole. And here we have a different components of North Pole and different kind of ice. And the nature of this ice is very different. First, we have, for example, Greenland ice sheet. This is a kind of ice on the land, and this is the different thing because we have another kind of ice on the ocean, and ice on the ocean and ice on the land is really different one. I mean, the composition, the chemistry, physics, everything is different. And also you have some kind of frozen ground called permafrost. So, but they need to understand, but if we have the Arctic Ocean and it's just freezing, and we can see Arctic sea ice on the surface of the Arctic Ocean. And why sea ice is important in the climate system? Because it covers a huge area of the Arctic Ocean, and this is a boundary between ocean and atmosphere, and all these processes related to the weather changes actually may be driven by this interaction too, like sea ice, ocean, and atmosphere. Also, it's contributing to the ocean water circulation at the global level. And it's due to different, again, physical and chemical reasons. It's changing. It may influence on ocean circulation. And it's a driver of different processes in the whole climate system. And when we can call sea ice as an indicator and agent of climate change. And this is a nice picture taken from icebreaker. It shows all these important processes. This is sea ice. This is area where sea ice is melting. And when the ocean here and the heat exchange, gas exchange. So very important indicator in the climate system. And now I want to show you a short video from NASA how ice is melting during the summer season. You see, it's melt season. It's starting sometime in March, and actually it's developing. And you see the dates here, June, and see by the middle of summer it's disappearing. Ice cover is disappearing because it's getting warm and it's melting and it's shrinking. The ice cover is shrinking. And here what they see, it's a really modern data. They from September 18, it's this year. And the yellow line is the average sea ice minimum in the Arctic Ocean during 1981 and 2010. And usually this is the average line, the average cover, the average area where sea ice exists during summertime. But here, you see, this year, it's the area less than the yellow one. So again, it's a good sign, warning, but something happening in the climate system. Ice is melting very rapidly. And why actually it's really important. First, we need to understand how it's changing, how the climate system is changing. It's simple to understand. Again, I will show this video because the ice begins to melt because we have some sunlight, what actually reflecting from the surface of the planet and actually from the surface of sea ice. Can run this again. And but if sea ice is melting, the ocean reflecting less energy, and it's reflecting less energy, it's warming up because energy is the driver of this temperature growth in the Arctic system. And this event called sea ice albedo feedback. And here, if you need little bit math, I can show you the little equation. We can use words to describe the temperature changes in the climate system because we have a difference between total incident energy and total outgoing energy. And this is the little formula that you can use. Basically, this formula is very important for climate modeling and climate prediction because many climate models, what they use to predict climate change in the future, were based on this so-called energy balance model. And even here, we have a very simple equation, delta T. The temperature change is the difference between two kinds of energies, but you can extend it and get more equations and then solve some kind of problem, how temperature changes and predict these changes. And generally, because sea ice is a good reflector, it acting like Earth refrigerator. It's saving cold on the surface our planet, because it's reflecting solar energy. If it's not reflecting here, if the ocean is absorbing the energy, so the ice is melting faster, and ocean is warming up, and the atmosphere is warming up, and then finally we can get like free ice planet. What could happen in the past in our history? As well as there is another state of the climate system, so-called snowball Earth, when the entire planet can be covered by ice and reflect all energy back to space, and when actually it will be not a warming planet, it will be a frozen planet. How to describe mathematically this phenomena? They use a simple parameter called albedo, and here there is a formula for the albedo. It's a ratio between reflected sunlight and incident sunlight. For white surfaces, for surfaces what reflecting light's energy very well, the albedo is actually pretty high, close to even 1, because if you have 1, albedo 1, it's ideal surface what reflecting all lights, all energy. But if albedo close to 0, it means your object absorbing energy, like ocean, like land, like any black object absorbing energy. So, and because sea ice and snow, we have a high albedo, the energy is reflecting and going back to space. And now I want to stop here and ask you, you can find the link in the chat, or just go to menti.com, put that code, what you can see, and I have a question for you. Name an object near you that has a high albedo. Any object what is close to you. You can just put the name, and you'll see on the slide, see your answers. Or you can also drop your answers to the chat, for example. But think about, again, high albedo when it's reflecting lights, reflecting well, right? It's a white surface. And low albedo, it's a black surface, and it's absorbing energy. Yeah, we can let's see what we have. What do you think, Andy? What is object? Can you hear me?
How about the whiteboard in my office?
Yeah. So let's see if you have answers. Somebody send it. Okay. Okay. Whiteboard, window. Yeah, it's interesting. The window, it's reflecting and energy, reflecting sunlight or absorbing them. That's also a good question. What kind of window we have, right? Because it's acting like a lens or not like a lens, right? Pavement. Yeah, you can be more active, and the sea. So pavement, it's the what color? It's black, I guess. And it should absorb, right, the energy. It has a lower albedo, I guess. Okay, so if you have any problems with that survey, let us know. I want to just update again and see more answers. Just 3 of them. Okay, you can keep going and drop your answers. So yeah, more grass in the garden. Grass is pretty dark, I guess. It has a low albedo, right? Because high albedo, it's reflecting, it's white surface, close to 1. It's high. Low albedo, it's close to 0, right? Okay. So yeah, we'll see. Maybe we will get more answers, but let's keep going. So as I said, this is so-called sea ice albedo feedback, when the ocean absorbing energy, ice is melting, and less ice you have on the surface. And you can see the huge area in 1980s, red and white, plus now you see what happened in 2012. So the difference is a huge one between past and now, because there is sea ice albedo feedback and ice disappearing due to this feedback. And again, because ocean absorbs more heat, temperature rises, sea ice melts, and surface albedo decreases, because everything going to be dark and actually absorb this energy, and ice is melting more. But it's the ideal option for sea ice, because we study sea ice, the model sea ice, like ice pack. The assuming ice pack is just a poorly white surface, and energy, sunlight just reflecting and nothing else. But in real life, sea ice surface looks like this one. And these elements of a beautiful mosaic of sea ice, it's so-called melt ponds. It's like real ponds after you have after rain ponds, and here some kind of such ponds too, but not after rain. How these ponds forming? I show a little video. If we zoom in, this is the ice surface, and again solar energy is coming and sometimes reflecting, but sometimes is actually melt the ice and snow on the surface. And it can be a very long process, and we can get big holes on the surface, or sometimes you can get these ponds. So ice pack is not fully melting. It's just some ponds on the surface, creating some ponds on the surface. But if it's really huge energy coming, at some point ice can melt entirely, and when these holes appears, holes, ice flows, and so on. But many such ponds appearing on sea ice, and again these ponds just like little melt water on the surface of ice pack, like our ponds on asphalt, for example. Same idea. But sometimes, yes, it's very strong energy coming. You can actually break this ice cover up and get holes, but they don't care here about these holes. They just care about these ponds. And if you go back to this picture, many years ago, when just we didn't observe climate change, very what happening fast now, the number of ponds, it was really small one. And by now the number of pond coverage on the surface, we have many ponds. And ponds is all ponds of water, and water absorbing energy, and we have low albedo. This is the real image from the Arctic, and you can see albedo of the ice, this area point and snow 0.67, albedo of melt ponds 0.27, the albedo of the ocean 0.18. So albedo of this pond pretty close to the albedo of the ocean. Again, it's water is dark and absorbing more energy. And you can see nice picture here. Albedo in the beginning of summertime is pretty stable, but at some point when we more ponds appearing, albedo just starting to drop down. And at the peak of the melting season, we have lowest albedo in the system. More ponds on the surface, the coverage close to 75%, and lowest albedo in the system. So we can say these melt ponds are dangerous, even it's on the surface. Ice pack is not fully melting, way locating on the surface, but it's decreasing albedo, and we need to study them. How to study them? Because again, I'm not just geoscientist. I'm not going to the Arctic and I don't know, make some experiments. I'm studying these ponds like mathematician. I look from above, from helicopter, for example, what is flying above the Arctic surface in the Arctic Ocean, and above sea ice, and I see beautiful patterns, beautiful networks of melt ponds. So it's a height of helicopter or drones flight. And instead of just studying every single pond, I really interested to study the geometry, because mathematics studies geometry, and this is kind of not geometry what we know, right? Triangles, rectangles, and blah blah blah. It's some kind of interesting one, new one, but we need to study it. How to study this geometry? So to study this geometry, we can recall or introduce a new word in geometry. Maybe you didn't hear it before, and this word is fractal. Fractal generally is not really well-defined still word, but generally we can say is a pattern or structure that looks similar when we viewed at any spatial scale. So we can see such a nice curve. We can zoom in and we can see here the same similar geometry. We can zoom in again and see similar geometry and so on. Many objects in nature fractal objects, so they have self-similarity. Zooming in or zooming out, the geometry, the shapes of these objects, they'll look the same. And many ideal objects in geometry also self-similar and fractal. But definitely these ponds, what they look here, maybe that they're not really like a fractal object, but to study their geometry, we can use one interesting parameter what any fractal objects or non-fractal objects can be described from. This so-called the fractal dimension. Fractal dimension is a ratio between perimeter and the area of our objects. For the simple shapes, we can find the perimeter, right? Or it's the sum of all sides of rectangle, this one, or square here, this, and it will be the perimeter. But the area of a square, it's L squared, right? The side, L is the side. So area and perimeter, two different, absolutely different parameters, as you may be studying geometry. And usually we try to find perimeter of triangle and the area of triangle, or so on. But how to find perimeter and area of such a wiggling objects? We cannot actually do it definitely. And instead of measuring perimeter and area, we measuring this parameter called fractal dimension d. For the simple curves like lines, circles, fractal dimension is 1. For more wiggling object is a non-integer. That's an idea. And for more space filling curves in 2 dimension, the fractal dimension will be 2. So fractal dimension can be between 1 and 2. And for clouds, for example, it's 1.35. 1.35. Again, I want to repeat that fractal dimension is just a parameter what can help to study geometry if we cannot measure perimeter and the area directly, because the complexity of our shapes. And when instead of that, we can use this d fractal dimension. It's a second formula what I want to show, a simple one, how to measure a fractal dimension of a square. And if you're really interested, you can find in Wikipedia fractal dimension of many different objects. Okay, so the points, what we have, they like wiggling, they have wiggling structure. And let's say we also can see how we geometry is changing from the beginning of melting season to the end of the melting season. And at the beginning of melting season, these ponds are little like circular shapes. After they developing to big complex network. And when using these helicopter images, we can compute perimeter in area of them. And instead of, because perimeter and area just this plot what doesn't show anything good. But if we transform it to fractal dimension, we can get very nice curve what actually have a transition at 100 meters squared. So it shows at 100 meters squared, these points from isolated circles becoming really complex wiggling networks. And it's really interesting, really interesting result, because it's not happening for every object in the climate system, for example. But we need to understand again the fractal dimension of these points is changing, and it has some critical transition at the area 100 meters squared. So this is the parameter what we can use to describe melt points. And also, if you look at the melt points, at this scale is kilometers of all these points. And as I said, we're changing properties of the like albedo, we're changing it because we're absorbing more energy and we're lowering albedo. It's called albedo is the optical feature, optical property of the material. And in physics, we have so-called many objects and optical objects, what actually changing light, right? Feature of this light. For example, thin silver films, they look like ponds, and also if it's a very thin silver film, and if you drop some lights on that surface, you can see how these patterns here change in reflectivity of this light. And this silver film are very important, in industry and in material research. And also the patterns on the surface of silver film have very complex wiggling geometry. What we can actually we can build the bridge between silver films and meltpoints. In a few seconds, I will show how to build that bridge. But first, I want to ask you the next question. Summarizing everything about meltpoints, let's guess what is the depth of a meltpoint. So in meters, again, if you can go to menti.com and put your numbers, your guess. So we can do it. We can see you're guessing any numbers. What you think? What is depth of meltpoint? Okay. You have one point as a point on the surface ice pack, but ice pack is not a thin one. It has the depth few meters. Could you guess what is the depth of melt? Oh, somebody said 1 meter. Who else? Andy, do you think we can find a Loch Ness monster in a melt pond?
No, how thick is the sea ice? That's the first question to put a pond into it.
Yeah, the sea ice, actually ice packs is, as I said, few meters. It's very variation depends. Yeah, how it depends what the thickness, but it can be from 1 to 4 meters even. But we actually, yeah, thinking about the depth of a melt pond. Yeah, maybe indeed we can find fish whale or something like that. Or it's like a buff for a polar bear, for example. So I see many answers coming. Yeah, I'm guessing we're doing in meters, right? Everything from 1, 2, 3, 4, 10. Anyway, it's first I want to say it's hard to say definitely, because you need to go to the Arctic and you need to measure depth of every pond, and after that find something average. But generally the observation shows from the Arctic, from people who made it, it's from 0.5, 0.2 meters to maybe 0.8 meters. So not really deep one. It's like kind of shallow water. And I don't think you can observe any live creatures in melt ponds, like big big creatures like fish or polar bear or something like that, because the depth of the pond, yeah, it's not too big. But you can find many microorganisms like algae, for example, phytoplankton, and other benthos and other kind of creatures in these ponds. Okay, so we are coming to our final point, how to model these ponds. And actually, I want to put a bridge between silver film in physics to the ponds. But they have different scales, ponds kilometers and microns for films. And these films usually they have magnetic feature. And let's recall what is a magnet actually and what's going on with magnetic materials. So they have a real magnets, right? And they attract some metal things. But sometimes some metals were not attracting and some were attracting. And at some point, magnetism is such kind of feature that you can obtain and you can lose. This nice experiment, it shows here they have a magnet, very strong magnet. Here, this is a nickel, part of the nickel object. So in reality, nickel coin, for example, if you take a nickel coin, it would be attracted by this big magnet. But here we have a candle and this flame, and once magnet attracting this actually nickel, and it's staying a little bit under this flame, this magnetic feature is losing, and this magnet cannot attract this nickel anymore, and it's going back because it's losing magnetic feature. And after some time, it's again collecting this magnetic feature, and when again this big magnet try to attract this little nickel. This is some kind of feature of many materials. They can get magnetic feature and lose magnetic feature. What's going on here? In physics, we actually know magnet actually they can be represented like a set of atoms in the lattice, and these atoms can act like little tiny magnets. And here I show one. Atoms or electrons, because they are rotating. This is a magnet, and we know magnet has a magnetic field, and this magnetic field has two poles, north and south, right? And when atoms or electrons and magnet are spinning, they also created magnetic field that can have different direction from south to north or from south to north this way. Depends on the rotation of this atom or this electron, whatever we have. So, and the idea is magnets, these tiny little magnets inside of the nickel, for example, the material called nickel, they forming magnetic fields because they have these magnetic features. And these little tiny magnets, they grouped in domains because it's easy to have better neighbors that looking the same way, right? For example, from this looking up or looking down, some of them. Again, the blue one is south, and white and red end is north. So, and what's going on in this experiment? They have a big magnet, and magnet attract this nickel. And when, look, the Miss magnet has a red side, what is the north of the magnetic field, right? And because, and these guys, they have a blue one, right? The another one, because a north attracts south, right? It's in electricity, they know like different sides of the magnet, they attracting, and other sides, the same sides, they don't like each other, and they actually pushing away each other. And then what's going on here? Magnet actually attracting these little magnets inside of the nickel, but now the object in the flames. And when the temperature is increasing, right? Because when it's fire and you increasing the temperature, and when what's going on next? These magnets losing direction because they had a nice direction here, but now we're losing this direction at some kind of disorder in this system. And when the magnetic feature disappearing, and when the magnet falling away, because they not actually really order it like it was before, and we're not really looking forward to attract this magnet, because now the temperature in the system is increasing and they have more disorder. They want to do whatever they want, but more than to be attracted by this magnet. And again, finally, this feature appearing because temperature is decreasing, it's cooling down, and magnets again try to sort everything out and align all together, and they want to be attracted by this magnet. This is the idea that the temperature can change the features of such a system. And if you watch sea babies and a night garden, you know we have two types of kind of neighbors where porcupines and wattingers, and one of them like red and now one blue. And when if we represent a magnet, we also say we have a like a home for them, a lattice, square lattice, and some of them wattingers, some of them porcupines, and they neighbors. Again, I'm showing what is inside of this magnet, what we saw on the previous slide. And some of them have a position aligning, looking up, and some of them looking down, And it's a different position. I can call S, for example. This guy look up, but in the moment it can look down because of this temperature change. And from porcupine, this guy become actually Wattinger, changing color. And if I take a next position for another error, I also can be red, and afterward I can be blue, And this going on with some certain probability. So it's not a regular process. All these guys changing colors, flipping with some probability, and this probability depends on the energy of the system. And this is the main beautiful formula what can help us to model sea ice and magnets and everything. It's the energy of such system. And just quickly show you what it means. It's just a simple things. We have a product. It's a S is the tiny magnet position. It just can be up or down, +1 or -1, depends what color it can take. This is the neighbor position. If you have this tiny magnet here, the next neighbor is here called N, and it has another position looking down, it will be -1. And when this guy is how they interacting, some kind of law of interaction. You interacting with your neighbors, right? And we have some rule how to interact with our neighbors. And this parameter will be this rule. It may be very complicated mathematical formula. Here is how big magnet impacting on our tiny magnets, how it's interacting, attracting. And so finding some probability when these guys looking up or looking down, or lining up or lining down, we can get such a model and model these domains, magnetic domains, what I said. And you see, depend on what they have direction of spin, we can of these errors, we can actually model clusters when they all align up or align down. And when finally, if let's say this guy, tiny magnet looking up, and we call it melt water, or if it's looking down, we call it ice, they can get same model, same equation, apply some equation, but sea ice. And here I want to show this model for melt ponds, what we can obtain using that single formula, an equation for a beautiful mosaic of sea ice. And the equation again is the energy, and this energy allows to model these patterns, the distribution of these patterns. And going back to the fractal dimension, I said the observed fractal dimension for real ponds like this on the picture, it's like that nice curve. And for our model, that nice curve, why we did it? Because we want to confirm our model works. Because all models should work. We should actually verify this model, what they are working.
Okay,
and when yes, and yeah, I'm
run out of
finishing.
time now.
Yeah, I'm finishing. Finally, we can apply this beautiful equation not only to magnets, meltponds, but also we can describe tropical storms or pistachios tree bloom using a just simple equation, how tiny magnets, ponds, and pistachios trees and so on interacting, and in how we're interacting. Thank you.
Okay, thank you very much, Ivan. So hopefully you all found that fascinating, seeing all these connections between magnets, the melting of ice, the ponds on the Arctic, and fractals. So we've got lots of ideas and words to go away and look up and think about. So thank you very much to Ivan, and thank you very much everyone for watching.